Hello everyone, and thank you for tuning in once again to the Group 3 podcast. This is a show where we interview working mathematicians about what it's like to do research for a living. My name is Logan, and today we are joined by Dr. Monica Nevins, professor here at the University of Ottawa. Dr. Nevins obtained her PhD in 1998 from MIT in pure mathematics, and since then has gone on to publish nearly 40 works on a myriad of subjects, including p-adic number theory, representation theory, and cryptography. So without further ado, thank you for joining me today.
Thank you.
Okay, so I guess we'll just jump right in. Could you talk to us a little bit about your field of research, and how would you describe it to a non-math person?
When you ask, how do I describe my research to a non-math person? Like, that's a big question, and I'd say that question usually leads to my trying to persuade a non-math person that there's even something to be researched in mathematics. I mean, we all come away from high school thinking that it's all been figured out, and we're doing this stuff from 1,000 years ago, and we're calling this the mathematics that we're teaching in high school. And so usually when I have to talk to a non-math person, my opening will be to talk about that part of my research that's in cryptography, because I find that one a much easier link and something that they can attach to much better. That said, I tend to think of myself as doing cryptography on the side. It's a passion, it's something I love, but the stuff that I take most seriously in my research is my p-adic representation theory. And that one, I don't manage to explain to non-math people, but I do talk about that. So where it comes from is if we're thinking about groups, we think of groups as being symmetries of objects, and then we want to understand these groups. But groups are horrifically complicated. I mean, especially these infinite groups that have topological structures and so forth. But the way that we get at them is by representation theory. We make the groups act on linear spaces, thus transforming the problem to linear algebra, and everybody knows that linear algebra is just fabulous. So representation theory is about that. And the groups that I like are ones that are a bit like the Lie groups that were discovered like 150 years ago, that arise from physics, but have in the last 100 years we've realized that we really want to understand them over a different set of numbers, these p-adic numbers. Now, when I talk to people about p-adic numbers, that's where things go off the deep end. Either you're willing to say, yes, that sounds really exciting, or you're thinking, like, that's a weird set of things to do. But it's just looking at the rational numbers from a different perspective. P-adic numbers are way cooler than the real numbers. Let's just be clear on that. It's much more fun than dealing with the real numbers. So those groups are just interesting, but we're still acting on complex vector spaces. So, piece of cake.
Okay. So I want to talk a little bit more about these p-adic numbers, because I'm not completely familiar with them myself. Could you talk a little bit more about what they are, maybe how they're defined, or is that too high level?
It'll be fine. Yes,
okay.
Let's do that, because everybody should become a p-adic number theorist. So the deal is, you remember how we got to the rational numbers. In fact, probably cavemen got to the rational numbers. We were, in some fashion or other, because that was perfectly reasonable. But that leap from the rational numbers to the real numbers, you remember it from second year analysis or whenever you learned it, that's like a huge leap. You got to do these sequences, and Cauchy sequences converge, and it's not natural at all. But the ingredient there is the notion of distance. And so we decided that rational numbers mean the distance between points on a line or so forth. We're thinking in a very Greek kind of way. Well, we are the 21st century. We don't have to think of distance that way. And one other way you could think about how close two rational numbers are is about how divisible they are by a prime number p. So pick a prime number p and look at a fraction and see how many times p divides the numerator or the denominator. Put the fraction in reduced form, and you can have like the degree, top or bottom. And with the p-adic numbers, you say that a number is very big if p divides the numerator not at all and the denominator a lot, for example. So 1 over 9 is a big 3-adic number. Whereas 9 would be a small 3-adic number. So the more divisible I am by p, the smaller I am. So then you decide, well, that's a distance, and you do all the math and you figure out that's a great distance. It's multiplicative, it satisfies the triangle inequality, and so you can do that whole Cauchy sequences converge thing, and you get these beautiful p-adic numbers. And they have really cool properties, two cool properties. First one would be that if you're trying to figure out if something converges, a series converges over the p-adic numbers, it's enough to check if the terms go to 0. Now, how good is that? I mean, this is like everybody's dream.
That's
so
really cool.
because analysis is a lot simpler. And the other cool thing about them is it turns out, and a variety of things, like the Hasse principle would say, if you're trying to solve a problem over the rational numbers, sometimes you'd like to transfer that to a problem over the real numbers because you can use analysis and so forth. But then you lose so much information. But in some reasonable way, if you would look at it over the real numbers and all the p-adic numbers as well, then you might be able to actually solve the number over the rationals. So this extends to ideas like trying to understand the Galois group of the rational numbers. That's a very big problem. Or trying to understand quadratic forms over the rational numbers. You can look at them over all these p-adic numbers. So it's the whole rest of the picture that we weren't seeing when we were trying to look at just the real numbers.
Okay. So I guess the main idea then is you want to use these p-adic numbers to get some kind of nice notion of distance, and then are you using that then to make or construct some kind of topology on these groups that you study?
Oh, certainly, yes. So with that notion of distance, I have a notion of topology on my p-adic numbers, which is a really wild topology.
Yeah.
It's so how about there's lots of compact open sets. And that's a surprising thing. But the idea is that your distances, though I didn't tell you what the distance was, but the distance is always a power of p. And so you have a discrete valuation, a discrete valued norm. And that means that all my open balls in my topology are either going to be size 1 over p or 1 over p squared or p cubed, and they don't overlap unless they're equal to one another. I mean, these are just amazing properties of this really weird topology. The p-adic numbers are like a Cantor set, topologically speaking, but they are locally compact, which means you can do all that good analysis like integration, and so the topology feels a lot different than the real numbers. But then surprisingly, and because of that connection with the rational numbers, like a lot of the theorems we have in Lie groups over real numbers are also true for totally different reasons for algebraic groups over p-adic numbers. So that's kind of a fun mystery.
That's crazy cool. So actually, there's another example of this kind of like discrete topology, and on the integers that I recently found on. Are you familiar with ProofWiki?
No.
It's just kind of like Wikipedia, but for math proofs, and they've got like a proof of the month that they feature on like the main page, and it's a proof for infinitely many primes. And I don't remember all the details, but what they do is they construct this topology on the integers, and they define open sets in some way based on the properties of these sequences, and from that you're able to deduce that there's infinitely many primes. So I think that's really cool, and I don't really have a lot of experience with like these discrete notions of things like distance and how those can be used in topology, but I think that was my first introduction to that. So I think I'm going to look up p-adic numbers after this and see how those apply a little bit better. But I want to move on just a little bit to talk something about your work in cryptography. You said it's kind of like a hobby. But actually the last person I interviewed, just the floor below you, Dr. Anne Broadbent, she also does cryptography, but she's looking at more like quantum cryptography. So I asked her about, some of the differences between classical cryptography and quantum cryptography, but I'd like to hear it from you, because I'm assuming, do you work on classical or quantum cryptography?
My world is classical cryptography, and
that's what I figured.
Yeah, and I don't know how to characterize it, whether it's a hobby or a second life, but it is. So how I got into cryptography in large part was through students. It is hard to recruit students to work in a PhD or in a master's in p-adic representation theory, because there's just so much background you need. So and if you're going to recruit a student early on, well, something cool like cryptography, which has all those great algebraic methods, comes in. So indeed, so Anne is amazing, and her work in quantum cryptography is just right at that cutting edge, and it's kind of about where classical cryptography is thinking about its big challenge as being. So we understand the quantum computers are coming, and therefore we should be thinking about developing as many different classical ones, because I have to think that the quantum computers for a long time will not be everybody's desktop computer. Mm-hmm. And therefore we're all going to need to have cryptography that's stable and strong. we're hoping the researchers will help us figure out which ones of these classical systems will survive the Great Divide. And so my interest is in exploring lots of different lesser known cryptographic systems. So I spent a lot of time with some students working on NTRU, which NTRU, and people say it's number theorists are useful. It's a lattice-based crypto system that's just has all these fabulous algebraic tools in it that you just absolutely adore, and you just love how it all fits together. I mean, RSA is beautiful, ECC is beautiful, but I love digging through the woodwork and finding other crypto systems that are based on other novel algebraic ideas, and just trying to see how we can push it a little bit further. And I think everybody should. Like, there's mathematicians working on this, and there's computer scientists working on this, and everybody has their own perspective. But our perspective as mathematicians is going to be, well, where's the structure here, and what's good about the structure and what's bad about it. So
okay. So what's the coolest one you found so far?
Well, I do like that homomorphic encryption. So I know Anne has a quantum homomorphic encryption, or is talking about that in a great deal. But very recently, like 10 years ago, recently in mathematical scale, Gentry came up with a notion of fully homomorphic encryption, which would allow you to do group operations either in the clear or on encrypted data. And I think group ring operations, actually. And the whole process of that, to figure out what he did and to understand that process is putting so many different details into your head at once. And if I think, what do I like about doing mathematics? It's when you have to put 15 different layers in your head, and you have to have them all in your head at the same time, and then you can see it. That particular moment is what I like the best.
All right. So the other thing that I was talking about with Dr. Broadbent was how like classical cryptography relies on, or at least like RSA schemes. I'm not familiar with all the other ones, but it relies on like how computationally complex some of these things are, and computers just can't do them. But with quantum cryptography, we're looking at fundamental properties of like these particles, right? So it's like nature-based instead of math-based in a sense. That's we're capitalizing off of nature and not math. And for that reason, Dr. Broadbent was arguing that it's superior to classical cryptography. But as someone who leans more towards the pure math side, that doesn't sit well with me. I think math should be better than nature. So I was wondering if you could talk a little bit about the classical side and whether or not you think that'll hold up against quantum cryptography in the long run. All
right. Well, I mean, although quantum cryptography is based on these weird properties of nature, at the core, it's still going to be, it follows certain mathematical rules. So I think it'll be completely mathematical in the end. It's just we have different ingredients that we get to play with. And you're right, maybe we're not going to base it on factoring large numbers. That's certainly not something that's going to be there in the quantum world. But anything clever we do will end up I think will end up being a mathematically based thing. To understand why it's working, to understand the rules of quantum computation, I think is going to be a very mathematical subject. I'm excited to see where that starts entering our curriculum, and we start really thinking about what computation means in this new world. Classical will always be there because we're just not going to have that many quantum computers for the foreseeable future. So, and we do need so much cryptography these days, and we need it fast, and we need it between any two people. And I think there is a strong potential that we'll have post-quantum classical cryptography. So crypto systems that are, say, lattice-based right now, that's the best post-quantum guess, that are no faster to crack than a classical computer could do, because there's no particular quantum algorithm that's been discovered yet that could crack them. I don't know how to predict what is going to be the kinds of things that quantum computers can crack and can't. I think that's the most exciting area of research, to understand what are the limits of quantum computation. What is P equals NP? What is the QP and QNP? What's that all about? But we are definitely at a point where all the computers we have are classical, and these are the ones we're developing, and I think there's a lot of potential that everything we produce, even if in the end we all more or less have quantum computers, we'll be using many of these algorithms, I think, to produce quantum cryptography in the future. But it'll still be based, like there's still going to be a lot of classical cryptography.
Okay. Actually, just want to go back a second to the p-adic numbers because so we talked about quantum computers here, small particles. Those are important, and I was reading through some of your webpage, and you do a really great job of explaining it to explaining what you do to a broader audience in some of the applications. And so we use these p-adic numbers to have a notion of distance, but you've written that the p-adic numbers can help physicists deal on scales where notions of distance don't even make sense. So how does that actually work? Because I know that there's like the Planck length, right? And below that, distances don't make sense from a physics standpoint. So how do the p-adic numbers make sense of it?
Well, I certainly hope the physicists figure that out soon. So the distance doesn't work in the classical sense, but the way the distance is working out is like an ultrametric distance, like a p-adic distance. But one thing that bothers me with that association, I mean, it's there. They can see that the distance is something that is better modeled by something like the p-adic numbers than by the real numbers. But I don't see how the value of the prime is coming in. So I don't know if there is a step there that a great leap we're going to make. Either there's a fabulous prime, or in fact it's all primes at once or something. But that the notion really is. So the notion of distance over the p-adic numbers means that 2 points, any 3 points make an isosceles triangle. I mean, this is just bizarre. Like you can't believe this if you're thinking of the real numbers. But it's that either I'm in the epsilon neighborhood of a point, or else I'm a certain distance away, and the epsilon away. It's a really incredible kind of notion of distance, and it's modeling different phenomena. And since we're getting to a point with quantum computing and quantum information theory and quantum mechanics and all these things where we really are changing what we think of distance, and I think p-adics have a chance of being the right model, but it's still in the future. But hey, that's okay, because we know that p-adic groups, or we know that real groups are very important for understanding symmetries in physics, and so now we're figuring out p-adic groups. By the time the physicists understand what they wanted to know about symmetries of p-adic groups, we'll have all the answers, and it'll be great.
Okay. So let's move on from this, because we've been talking about all this math stuff for a while. So let's talk about instead, when did you decide that math was the career path you wanted to follow?
Well, I knew that I wanted to study math in high school. I was clear that this was my favorite thing, but it didn't seem very practical. And so when I started my undergraduate, it was math, computer science, physics, and then physics. Well, that's got experiments, and they never turn out right, and it's just so awful. So it was down to math and computer science. It was the second-year group theory course. That second-year group theory course, we were learning about the groups from an axiomatic perspective and proving things, and this is what I've been waiting for my whole life. I mean, these structures in front of me, and the way you have it in your head, and the way you can prove stuff from them. This was eau de vie. It was absolutely magnificent stuff. And then, so I knew that math was for me, but I still thought, it's not very practical. What could you do with a math degree? So when I was picking my courses for third year, I picked, the applied math and the applied linear algebra. That sounds good. Like I'll get a job with that. And the director of the department, Henri Wang, and I have to thank him so much, called me at home and said, you've picked those courses and you shouldn't. How about you take, this ring theory course and this linear algebra course? And it's like, oh, okay, I will do that. And of course, that's the kinds of steps that led me on. In fourth year, again, a wonderful professor of my Lie groups course was was just talking to me about graduate school, and then I asked him, well, where would I go if I wanted to do graduate studies in Lie theory? And then he took out a piece of paper, which I have kept to this day, and he just jotted down some names of people at Harvard and MIT. And I was just so overwhelmed with that much encouragement and confidence. Well, I couldn't let these people down. And so I guess my story is that I just kind of got buffeted, and at every step it was just somebody being very encouraging and wonderful, and just continuing on this path, never believing that I could get to this end point of an academic career, which is fabulous.
Yeah. Well, that's awesome. It's great that you had those people to kind of push you along towards And then MIT, of all places.
A fabulous place to study. I highly recommend it because it's like being with the most amazing people in the world. And you feel like the stupidest person on the planet in comparison. And but everybody's excited about math, and it is a wonderful culture. And I see that in lots of different graduate schools where they really, you feel you're part of a club. And that's a really great experience.
Well, at Waterloo's got the biggest undergraduate math faculty, so you go there, and I had the same experience as you. I felt like the dumbest person in the room because there's all these great people like IMO gold medalists and that. But I mean, it's such a supportive environment. It's great. I love math people.
They are pretty cool.
Yeah, they're so nice. So. You've also done other things too, like not just sticking to mathematics. You've also done a lot of like community work, like reaching out and bringing math and science kind of into the public eye. You've done a bunch of different math talks for broad audiences. But in particular, I wanted to ask you about when you judged the Canada-wide Science Fair. So what was that like?
It was great. It was a lot of fun to talk to these very enthusiastic high school students who have... And we're doing incredible science at home. I mean, a level of science that I would think is university quality kinds of study and the right kinds of hypotheses. Very few math people doing these Canada-wide science competitions. I mean, truly we need more math in there. But great to see people so enthusiastic and questioning. And I'm sure that some of them secretly just want to study math when they come to university.
Were there any math, like, I don't know what to call them, like exhibits? Presentations?
No, I don't remember any specifically math presentations. The stuff that we work with is not tangible, and that's the whole point. I mean, all those wonderful things we deal with are things that we construct inside our heads. And the miracle is that we can communicate these things. We've developed this incredible language of mathematics that lets me, in some formal way share with you this amazing and elaborate structure that represents and that can map onto so many different things. So math is something I absolutely love, and I really, as I do these outreach activities, I want to help share what it feels like to do mathematics, because maybe that's something that isn't so easily shared. We have this feeling from school that math has all been discovered a few thousand years ago, and that's that, and maybe it's a bit torturous, and it's like, no, it's all the other cool stuff.
Yeah, of course. There's actually, there's a great quote by, I don't know who it's by, but it says that mathematics teaches us to say what we mean and mean what we say. And
yes.
I think that's a very apt way of putting how we communicate it. So, but back to the science fair, what do you think was the best exhibit?
Somebody was growing... Oh no, the coolest one was somebody was growing plants inside of a mix of dirt and also the stuff that you put in babies' diapers, like that soak up water. And then the idea was that it would soak up water, and in drought, it would slowly release that water into the earth around it. And, and she was proving that, okay, you can't grow the plant fully in the diaper stuff, but in a mix of dirt and diaper, it works out just fine, and it does survive drought a little bit longer. And that just tickled my fancy. So.
That's so cool. That's awesome. What a weird idea.
There's a lot of weird stuff
throw
in there.
Diapers in the dirt and grow plants in it. But I like it. We need that originality. So what was the first mathematical result you remember producing, even if it wasn't publishable?
So I can distinctly remember the moment when I solved the first part of the puzzle for my PhD thesis. I mean, I remember, I can have a vivid memory in my head of standing up, of the furniture in the room, of walking out, and just the sudden feeling of just having changed from being weighted down to being completely floating. And that being said, I can't identify what that result was. I mean, I know it was one of the cool things about figuring out how symplectic groups act on this very particular space, but at the time it was just something got a key turned in a lock and a door opened and the world was suddenly different. So I can't remember the result, but I can remember the feeling of getting that result. Mm-hmm. Yeah. Before that, like if you think of original results, it's all those little steps you have. Like I also go back to thinking third year university, third year real analysis, and you had that homework problem about supremums or something, and just I remember being obsessed with this particular homework problem, and just like absolutely like through the moon. The only thing I could think about. And then I got it, and I was just like amazed, and then I handed it in, and when I got it back, it was wrong. But that's okay, because the wrong was kind of an incidental wrong, and what I'd figured out was still true and was still real, and it was one of those epiphany kind of moments. Yeah. So yeah, proving a mathematical result, sometimes it's not so much that you've finally discovered it, but sometimes it comes with a little tinge of oh God. My friend Jeff Adler at American University calls it an epiphany. It's like an epiphany, except you feel like you should have known that like 3 months ago.
Yeah. Yeah, it's so true though, because once you prove something, you're like, oh well, it's obvious now. Like, how did I not notice that before? But yes. It's so easy to forget how long it takes you in the process of building everything up to end up proving the result. Yeah, it's crazy. So what would you say then is your proudest mathematical achievement?
A few years back, I had been working a long time on understanding something about SL2QP, or SL2 over p-adic fields. That's 2x2 determinant 1 matrices. That's a beautiful group. And I'd worked out the problem that I was working on completely in this one example. So I felt very good about that. But what felt really proud was then saying, okay, now what have I learned from this process, in this extensive and exhaustive process? What have I learned about the general case? And then just being able to sit down and having everything kind of fall into place, and figuring out, oh, I know all this about a certain class of representations of all p-adic groups. And it was beautiful for me to realize how all those months, and in fact years of training, had suddenly led to a moment when everything just clicked into place and the pieces were in front of me. So, and of course I really loved that paper. So.
Good, cool. So, well, the flip side to the proudest mathematical achievement is, what's the thing that's kind of like weighing you down, like that one problem that you wish you could solve but haven't been able to yet? So there's a couple of those. Okay, there's infinitely many of those. Specifically ones that I have gotten close to. So my first love in p-adic representation theory related to orbits of the group on its Lie algebra, and among those are the nilpotent orbits, and there's only finitely many, and so you'd think, well, that should be the easy case of everything that's going on. There is a huge theory behind saying that orbits should be associated to representations in a way that is analogous to classical mechanics should be related to quantum mechanics by quantization, and so the orbits in a lot of ways represent classical mechanics and representation theory quantum mechanics. So that said, there's this great analogy and the pieces are almost there, but the nilpotent orbits are the last stumbling block, and there was great strides made in this, maybe in the 10 to 30 years ago in that envelope, and now we're just waiting for the next great breakthrough. So every few years I go back and see what more I can figure out about nilpotent orbits, just on the hopes that I see that one more clinching detail that's going to help me really push it forward. Yeah, maybe that's my big one. Okay, very cool. Do you have a favorite theorem then?
So you asked this in advance, and then I thought about this, and it's just so hard to come up with your favorite theorems, but honestly, I confess, it's the baby theorem. It's the one that starts it all. Lagrange's theorem that says the order of an element in a group, or the order of a subgroup, will divide the order of the group. I mean, it's like the beginning of all the beautiful structure you have. It's like saying there's absolute order in this chaos, that everything is going to be rigid and beautiful, and the jigsaw pieces are going to click into place. It's a promise of so much more. So, yeah, my favorite.
All right. Oh, I'm looking forward to my group theory course next term then.
Very good.
So that should be fun. Do you have any math jokes?
All right, I do try to tell jokes, but I'm not a very skilled joke teller, but I will try to get this one right. Okay. So a biologist, a physicist, and a mathematician are sitting in a cafe across the street from a building, and they see one person walk into the building, and a little while later they see two people come out. And the biologist said, they reproduced. And the physicist said, no, measurement error. And the mathematician says, no. Just wait for one more person to go in, and then the building will be empty. Very good. You got that right away. I told that to a room full of mathematicians once, and lead balloon.
Well, mathematicians aren't very good with numbers. Well, actually, so just on math jokes or math entertainment, I noticed on your website you linked to a couple of math songs.
I love a cappella science, for example. I absolutely love everything that they do. And yes, I mean, isn't it great when somebody makes a math song? I mean, how often do you get something
There's not
like
enough
that?
of them.
Absolutely not. So a cappella science, and even though a lot of their stuff is the physics, but they even had a song about William Rowan Hamilton, so the discoverer of the quaternions, which I think is like, okay, all right, this is what we need more of. So I'm not sure that math makes it to popular culture. There's too much inside our heads and not enough that we can show outside.
Yeah.
But we got to hang on to the few references we have. So
I agree. I think there's probably a little bit more room for math in pop culture, but it certainly is an acquired taste. Okay, so do you have any mathematical heroes?
Yes, I guess I have. There's a couple of people that I actually met. One person in particular who passed away just a few years ago, Paul Sally. And he was a professor at the University of Chicago, a giant in my field of p-adic representation theory and characters. And he was called the math pirate of the University of Chicago. He was a person who was larger than life. I mean, he was, easily 6 foot plus. He had an eye patch. He growled at people. He was the most beloved person on campus. Not only was he a leader in p-adic character theory, mentoring so many people. I mean, there's so many people whose lives have been touched by him, both mathematically and personally. And he ran outreach programs for high school students in the Chicago area. He did so much and just had so much boundless energy. And I think that is someone I want to be able to emulate. Like, not just doing the mathematics for ourselves and do it so brilliantly, that would be lovely, but to also be so successful and so willing to share and to try to help more into it. So
That's incredible. Do you have a favorite story from math history?
So presumably among everybody's favorites is Galois. We have to talk about the story of Galois. So certainly I love doomed Galois and the idea of this young mathematician at age 20 writing down his greatest ideas. I love Gauss, who at age 6 solved his teacher's problem. These are the kinds of stories I will absolutely share with my students whenever I can. Hamilton, I think it's great. Mathematics as graffiti as a celebrated theorem. This is great. So he had figured out something called the quaternions, because he'd been struggling forever and ever to figure out how to multiply triples of numbers, because we can multiply singles of numbers, we can multiply pairs if we think of them as being complex numbers. So if you can do the real numbers and the complex numbers, what's the 3D analog of this? And then coming to the sudden realization after many years of thinking about it. Well, I think the story goes like he was walking along with his wife and she was talking about things and he was not quite attending, as he put it. And then he came to the bridge, and at that moment he realized that he couldn't do it in 3D, he had to do it in 4D, and he knew exactly what the relations had to be to generalize the complex numbers. And so he scratched them into the bridge and was like terribly happy. And to this day they have re-etched the graffiti into the bridge and put the plaque and everything. I think that's good. I mean, how often are mathematicians graffiti artists?
Yeah, exactly. Yeah, I think math history's got so many nice little nuggets that in here or there. Galois, great one. Hamilton, another great one. But you brought up his haha moment, his Eureka moment. So I'm wondering, because those can happen, the most unlikely places. I'm wondering if you've ever had a Eureka moment at a not obvious time.
Actually, the Eureka moments tend to happen at the non-obvious times. Like, it's just when you've paused and you're letting your mind wander a little bit. I mean, the number I would say that it's as I'm going to sleep or as I'm just lying in bed and staring at the ceiling that sometimes pieces fit together, that we're sitting in two different parts of my brain, and finally they wander close enough to connect. And those are amazing moments. I mean,
and you don't get any sleep that night.
You desperately hope you've written it down correctly. Yes. So.
Okay, for sure. So we were almost through all the questions. We just breezed through those. But actually, I did want to ask another one about p-adic numbers, which is related to something that I'm kind of interested in personally. And that is the Riemann-Zeta function. Obviously, all young mathematicians like, the Riemann hypothesis, shoot for the stars. But I've heard p-adic numbers have been used before. I don't know to what extent, but in studying, L functions and that sort of thing. Have you done any work with that before? Or?
I haven't worked with L functions myself, but L functions are a huge part of the big motivating problem in my area is called the Langlands program. And this comes from Robert Langlands, Canadian mathematician, who realized, or just, it's amazing, but he saw from one example what the general theory should be like. And the one example was class field theory, and the general example is something about representations of p-adic groups, or more generally, groups over the rational numbers, which we haven't gotten to. Should be related to representations of corresponding Galois groups. And the relationship should be made by L functions. So the L functions you get out of the Galois theory should map to very naturally defined L functions on the representation theory side. And that he could see it from nothing is amazing. And then the amount of mathematics that this has generated as people struggle against this incredibly difficult problem. And so I feel like we're all ants on a hill working on this massive, massive problem, putting all the pieces together. And yes, one of the pieces we'd want out of this would be the L functions and understanding this Galois group so much better, which has got to get us closer to the answer of what's happening with that Riemann hypothesis.
Mm-hmm. Well, hopefully, yeah. But yeah, didn't Langland recently win a prize for that?
Oh, zillions of prizes.
Zillions. He's super important.
Yes, and and there are these giants in the field who often are not as young as they say. They do say great mathematics should happen before the age of 40. I will agree. You can point to Galois, to Abel, to Gauss. But those are all from the dark ages, right? People died at 45 back in those days, right?
Yeah.
So well, maybe, not Gauss. But Abel and Galois dead at 20s or something like that. So we have this perception that great math should happen before age 40, but then you look at people like Paul Sally, like Robert Langlands, like Jim Arthur in Toronto, where they were just getting started at 40. And so I just want to say, yes, it's great that we have some prizes, and it's too bad the Fields Medal says let's cut them off at age 40. No more Fields Medals if you're 41, even if the stuff you do is so incredible.
Got 21 more years, so we're going for it.
Good job.
We'll see. But okay, so Langland, super giant in mathematics. Who's the most famous mathematician you've met?
A famous mathematician I've met. It's a joy to be in the mathematical circles because you get to go to conferences and just naturally talk to and shake hands with, all these great mathematicians. And you're giving a talk and they're giving a talk. And for a moment you're on par. Not that I can say I'm on par, but, meeting people like Jean-Pierre Serre, who a French mathematician, famous in representation theory of groups, has written so many books, really great stuff. Bertram Costant recently passed away, but he was at MIT and it just absolutely nailed the field, just understood all this orbit method is all from him. To point out one particular mathematician, we remember the theorems, we don't remember the people so much, perhaps. It's, I don't risk saying, one mathematician over another and trying to identify one more than another.
Fair enough. Okay, so my last question for you then is, what advice could you give to us aspiring mathematicians?
to definitely let yourself follow along and figuring out what you like best, because I think that different people will think in different ways, and mathematics is all about how your head is aligned with the subject that you're trying to take on. And I think, we love doing math. It's got to be releasing dopamine. Like when we're doing the good math, I mean, that's a high like no other. And you only find that by kind of being open to being buffeted, to following your nose, to seizing some opportunities, to play around with things, and just to have some fun with it, and taking your time to enjoy some of these things. Maybe taking the time also to be completely focused on it. When I think of people who are struggling with math, this is not the people who are aspiring mathematicians, perhaps, but it would be so much better if they could just dive completely in and feel as immersed in math. When you feel completely immersed in math, that's when things are really going to click together, and it'll be a lot of fun. So enjoy it, I guess, is my thing.
Okay. Well, thank you very much for coming on the show.
All right. Thank you.
All right. Take care.